Good evening, everyone, and welcome. This is Professor Thayer with you here today to talk about working with Unix. This is the third part of a three-part series. Let us go ahead and get started. I'm going to share my screen here with you, and let me put up my slides for you. So today we will be talking about working on the Unix cluster using Bash scripting. We will also cover working with the shell, which is a common task one would need to do when you need to submit your jobs to the queue. So in day one, we had a look at the HPC, particularly here at Wesleyan, but should apply to just about any high-performance computing environment. On day two, we talked about working on the cluster with text editors. And today, the third part, we will talk about the scripting and queuing. We will understand the queuing system, look at making some bash scripts, submit some scripts to the queue, and learn some more Unix commands in the process. So let's go ahead and get started with scripts. So the first thing I'm going to point out is the use of the hashtag or pound symbol. The job submission script typically consists of several parts, and the pound symbol is used for commenting in the Bash programming language, and it will be a comment, which means that it will not actually get executed. It's for you to make some notes to yourself. And we will see that you may also make some other kinds of notes using that as well. The first line is going to be called the Shebang Line. This indicates what script language is being used so that we can explicitly tell the operating system what code it should run in order to execute your script. The pound symbol in the first few lines at the top, without the blank lines after, will allow passing information to the queuing system that will not be executed as Unix code. So this is what I meant by it is for a comment, but you can also use it for passing information which will be ignored by a Unix interpreter, but may be interpreted by something to which you submit this script, such as the queue. The keyword bsub is going to be used to indicate that this is a bash submission script, and it will provide information to the scheduler, that is the software that's going to actually cause your job to be sent off to the queue to then go and get calculated. So that's how you will indicate to the scheduler to read it. So let's take a look at this in a little more detail and actually pull up an example so you'll know what it is we're talking about here. So the Shebang Line, as we mentioned, belongs at the top of your script. So here we see the Shebang Line appearing right here. We've been using bash scripts. We looked at a little bit of these last time, but we didn't really talk about them too much. There are other kinds of programming languages that could be used. For example, there could be Perl, Python, C, C#, C Shell, Corn Shell, and many other programming languages. Programs written in the Unix environment should begin with the Shebang line to indicate what kind of program it is, which is this line right here. The pound symbol, which is a little bit dark and hard to see here, but there is a pound symbol here. The cursor is just on top of it. Indicates it is not to be directly interpreted as part of the Unix program. The line must appear as the first line in the script. It cannot appear anywhere else because the Shebang line will only be interpreted if it's the first line. The exclamation point, which is the bang part, or what gives the bang part to its name, is used to indicate that this is the Shebang line. Then the path, which is right here, is given to indicate what should be used to run this program. So there could be some more script down here, which we will work on developing in the subsequent slides. The Shebang line indicates that this is a bash program, which should be executed by the by bash, and it's located in /bin/bash. So remembering from when we discussed the directory trees, what this means is we begin at root. So this is an absolute path, and it would be in the /bin/bash directory. So it's possible that you may have the executable located someplace else on your machine. So you may just need to find out where it's located, and you can do that by using the cd commands and the ls commands in order to just find that on your system, but there's a good chance that it is also located in the /bin/bash. What other programs could the shebang point to? So here, this just gives you a little bit of an idea on how you could go through and discover what else you might wish to point to. Most programs that shebang would point to should be in a system-wide program installed by the system's administrator in some common location. /bin, which I have changed directory to bin and use the ls /bin right here so that I could see what's located in the bin. The other location you may find it in is /user/local. Issuing the ls/bin will show in green the programs installed on our cluster, and bash is one such program. So let me just this for you. And there could be other ones as well. Here is our bash right here in alphabetical order. The green is indicating these are things that are executable programs, and other colors are indicative of other kinds of things that are here. Note that we're pointing to the language of the script and not to any program that the script would run. So for example, inside of our script, we may be running an Amber calculation or a MATLAB calculation or a Gaussian calculation, in which case inside the script, it would be running the program, and that's not what we're doing. This is the wrapper script. So we're actually putting the shebang line in the actual bash script itself, which may then run another program, but we're not asking what's the language of something that it runs. We're asking what is the language of the script we're working on right now. So in many cases, it will in fact be bash. So let's take a look at setting your shebang line to something else. So let's say we want to select a particular version of Python as the language of a script. So we notice that both Python 3 and Python 2 are available on the cluster. We can tell this by using the which command. And we see that so when we use the which command, that will tell us which Python is the default Python. But we can also do which Python 2 for the older version of Python, because typically these days we're working with the Python version 3. I do believe 3.10 is the current version as of this video. That, of course, will probably be ever evolving, but pretty much Python 2 is not really being developed anymore except for applications using it. So you probably want to be using Python 3, but there is an awful lot of legacy code out there that still uses Python 2, and you could fall in this category. So how could you write a script and make it point to Python 2 instead of Python 3? Well, you can use the shebang line to do precisely that. So Python 3 is the default because that's the one that is selected when we just do which Python and we don't say which one. Suppose you want to explicitly select the older Python 2 for some legacy code. This could be done by putting that path in the shebang line. So here we're going to in fact do that. This can be done by putting it in the shebang line, and then we're going to put something for the script to actually do. So it's going to print hello world and is going to say that it's using Python version 2. And so this is a good test case because I have omitted the parentheses, which would be required for the use of Python 3. Now Python 2 could have some upgrades added to it to get around it, but for the time being, let's keep it simple here. So what we can do is we can execute this script, and in principle, as long as we have gotten to Python 2, we should get a hello world. But if we are in Python 3, it should produce an error because this is the wrong syntax for Python 3. This is one of the differences in the syntax between the two versions, which I just happen to know. And here we are going to execute this, and we get hello world from Python version 2, which means we have successfully done this. Now we're also doing this change mode, which I will tell you about in a moment. That leads us into the file permissions. So users on a cluster are organized into groups such as labs or classes. It's useful to allow my group members to read my files, like might make some templates, some inputs, scripts for them to use. And if they couldn't see it, then we'd have multiple copies on the cluster, which is really inefficient. And so what we would like to be able to do is to specify, like, members within a certain group should have permissions to all see some certain files. We can even change it so that they can run the code, and we could even allow other users to modify our contents, although this is not really advisable because really you should be the only one who is writing in your disk space. We may not want to share our work with all the users on the cluster, though. Who knows? Maybe you could have competitors, or maybe just other people aren't that interested in it. I mean, that's usually the situation in the university, is that you just want to share it with others that would actually be interested in looking at it. And most of the people may, for example, land within your group. That's the typical situation. So what you might want to do is to give read and execute permissions to other members of your group, such as my research students. Or maybe one of my students writes some code and they want to share it with one of their colleagues, one of their coworkers in the lab. And so they could change the permissions so that others in the lab could see. Like I mentioned, we should not give write permission to anyone else. Otherwise, somebody else could edit, change, or delete your files, or fill up your disk space with their own work. So usually people don't do this on purpose, but sometimes people are not that familiar with how to use Unix and could accidentally delete, remove, and so on your single copy of a very important file. So usually the better thing to do is to not allow write permission for your files. So permissions are applied in 3 ways. The permissions could be given to you for user. This means the permission for the owner of the files. So that's yourself. So you might think, well, that's silly. Shouldn't I, of course, just have permissions to do everything? Well, some files are not actually meant to execute, for example. So having an execute permission on a file that's not actually meant to execute wouldn't really make sense. And so this is the way that these things can be changed. You'll see in a moment that when you make a text file, typically it's going to have no execute permissions by default. And so that means that you would need to change the execution permissions in order to be able to execute that file. Because of course, all text files are not executable, only just the ones that are written as executable code, i.e. scripts. Then we have the group permissions. This is permissions for others in a designated group or groups, such as the lab members, to do something. And O is for other. This is the other people who are using the cluster who don't happen to be in my group. So for example, there could be another group in the physics department, and so they may not be particularly interested in our files, so they probably don't really want permissions to see our content, and we may not necessarily be reading theirs either. So you can change the other permission to not allow others to see the things on your disk space. So the permissions that can be given to user group or other are read. This means you can view the file but not edit the file. W is for write, which generally encompasses editing and deleting. So that's the one you really don't want to give out because you don't want others changing your files. Reading it only allows them to view it, but they can't edit. So that's the difference between read and write. Write doesn't just mean save, it also means editing. And as it mentions here, also deleting, which could be very dangerous. And X is for execute. This enables the file to execute. So we would need this to actually run some code to say that it's executable if you want to run it. So you can view your permissions in this way. You're going to use the ls command with the -l option. It does look like a 1. These are both lowercase l's. ls for list and -l stands for long, meaning it's going to give the full output information. So if you just do ls like we've seen before, you didn't get all this information, but this is showing you what an ls -l is going to give you. So there's in fact 2,888 files here. We're just taking a peek at the top ones, And we can now see the permissions. We can see my username. This is one of my groups, and then we're going to get information about the file size, when it was saved, date and time, and also some information about the name of that file. So when you just do a plain ls, you're just going to get the names of the files, which are being shown over here, but you're not going to get all this other information. So in terms of understanding what permissions are attributed to these files, that's where these columns over here are going to be useful. So the output's given in the order of read, write, and execute for each of the three categories. So in fact, the first one actually is to indicate whether it's a directory or not, so which is a folder. And so if it were a directory, you would have a D here, but none of these are directories. These are all just plain files. So you see those are all given as dashes. So dash means it's not assigned, and seeing the letter there means that you have that permission. So the first three are going to be for the user, that's me. And we can see the user listed here. So this means that for a file called emin1.in, this happens to be an input text file for an energy minimization. I have read and write permissions, but no execute permissions, which is fine because it should be just a text file. It's a text file to be ready to configure or run. So I wouldn't need to be running the file itself. And then we have also the, okay, so it goes UGO, this is user, right? Next three are for group. So of the group permissions, R, W, and X, I have only given out read permission, which means other members of my group could read this file. And in the other category, we also have just a single R, which means that others, any user on this cluster could read this input file. That also predicates that all of the path going up above it also is available to read. So you could end up with an issue where you think you have made a file readable to others, but if they cannot read the entire path to that directory, there could be a problem in the permissions to actually do what you want them to do. So that just gives you a little clue. All right, now here's one that's kind of interesting. So this is a run emin.sh. So this is the actual bash script that will actually execute the energy minimization, which will make use of the emin1.in as to configure it as the input for an energy minimization. But since this one is executable, and also notice that it's green color to help you spot that very readily, we see that I have read, write, and execute permissions. So this is user, and my group and other also only have read permissions, so they can't actually run this. Now I could change the permissions so that my group members could execute this script, or others for that matter. So that brings us to making a script executable. So if you create a script using the text editor, by default, it's not going to have execute permissions until you change the permissions for it to become executable. A way around that is if you copy another script, it's generally going to take the attributes that it has already in the copy. But if you just Emacs and give the name of a new script, it's going to just assume that it's just a plain text file and it's not going to be executable. So here is a script called test.py. When we create it, it does not have the execute permissions, which we see because ls-l does not have X shown. So here we make some script and we do ls-l test.py so we can get a look at what the permissions are. The user has read and write permissions, but no execute permissions. Others can read it and group can read it. And so if we actually cat the test.py to see what's in there, we see that this is just that hello script we had written in the previous slide. And so then I try to execute it in the usual way using the // notation. Recall the dot means the current working directory. So this says in the current working directory, and then slash is for that directory. Check for a script called test.py, and we get this error permission denied. And this is the clue that you do not have your permissions set correctly. So what could we do about that? So to fix the problem, we can change the permissions using the chmod command. So this is for change chmod mod for the mode. So you can use the plus to add permissions and minus to take permissions away. So the format is chmod, and then you select user group or other. You can actually pick any number of these. So you could do all UGO, or you could do UG, which is yourself, and the group, which is probably more common. And then you need to decide what you want to do. Do you want to do read, write, or execute permissions? And then you need to specify to which file this should be applied. So select which of the user group or other you want with the 1-letter code, and then you would select which of the permissions you want to change using the 1-letter code up here. So this is an example to add execution permissions to the user to this test.py. So here you see how we've put this in. We do chmod for change mode, and I have selected you for the user, myself, because I want to change my permissions. Now I want to add the execute, so I need to pick a plus, and then I need to pick X because I want execute. I already have read and write permissions, so I'm going to use plus X, and then I supply the name of the file that I want to apply this to. You could also have this target be a directory as well. Usually you wouldn't add execute permission to a directory, but you could add read permissions, because that would mean that you could open that directory up to be read in a path leading down to a file, for example. That's how you do it. So let's say you want to remove all permissions for other. Don't want anybody outside our group seeing our secret work. So here we would do chmod, and now we use O minus RWX. So O selects other, minus means take away the permissions, and RW and X specifies the 3 permissions you're taking away. So again, in these groups, you can use any number of selections. So for example, you can do chmod, and then you can specify more than 1 out of UGO, and then you can also specify more than 1 out of RWX. Obviously, it doesn't make sense, get our lights back on, to use the plus and the minus in the same line. So you have to use either plus or minus, and then of course you have to say to what you're applying it to. So here is our example right over here called we are missing the execute. So I'm going to do chmod, and I'm going to add execute permissions for myself. And I'm also going to just go ahead and add it for my group members while I'm at it. And then I will use that test.py. And now I'm going to issue the ls-l for the long listing of the test.py. And we take a look over here. And I, as the user, have RW and X permissions. Now, the key thing is that we have added execute. Notice that I already had the R and W permissions. I mean, if you reset it to the same thing, it doesn't cause any problems or anything. It would overwrite if you change it. And now also notice that it has turned this green color, which is really useful for you to quickly notice that, oh yes, now I can execute this file. So now we go ahead and repeat our call for the script. So we use the dot notation, the dot slash, and then test.py. And we see that now the script has worked and the permission error has gone away. All right, that brings us now to writing some bash scripts. So these, in fact, were some bash scripts, but there's a few more things that I want to focus on in this section. So just like Python, C, Corn Shell, Perl, and so on, bash is a programming language. It does tend to be used as a script more than actually for doing computations, because it's not particularly fast, and it's really designed to be used as a scripting language. It's a popular choice of language used to interact with Unix machines. Your prompt in the terminal is executing the bash commands on our machines at Wesleyan, and it is very likely that that is the prompt that you have by default on another machine elsewhere. So if you need to check, you can just type, check at your prompt to see what it is, and or if you want to go to bash, you just type bash, and that will switch your shell to bash. So you'd be pretty hard pressed to find a machine that doesn't already have bash installed. Well, of course, the Unix machine, because that's a pretty standard thing to find on any Unix machine. You can save commands you want to type at the prompt into a text file and then execute that, which is a script written in Bash, which we've taken a quick look at, a short one. You can write a Bash script to do tasks you would do at the command line, and so why not be able to save them and run them later? Job submission is something that you must use a submission script for, and these are going to be written using Bash. So if you're going to be submitting jobs to the queue, you need to learn how to make Bash scripts. Why should we create scripts? Why not just type it from the command line yourself? We might want to keep records of a procedure. We might want to automate tasks. It can be run at a later time, and you can also share this with others, which are all very useful things, especially in the Unix environment, which encourages collaboration and the use by multiple workers. So then, let's see how we could actually create a Bash script. Although the use of a Shebang line is not necessary, it's definitely recommended. And so we would start with the Shebang line, which we've already seen. Then we would enter the Unix command in the scripts. Notice we have a couple of other comments here, which are going to be ignored. But then we're going to have some commands of all the things we want to do. We need to change the permissions of the script so it's executable, so we can run the script, as we've just seen using the chmod. And then we can proceed the name of the script with the / to actually run the script, which we have seen anecdotally above. So the script is not in the working directory. The path to the script could be used, or you could change directory so that it becomes in the working directory. And then the / indicates the script in the current working directory, since the dot indicates the current working directory. So here we see we're changing the mode, and we've seen this before. And so here we could see that we could just take a look at these files, and this is how we would change the mode. So then let's take a look at perhaps creating some scripts that are going to be relevant for working in the HPC environment, which is the job submission scripts. First line is the shebang. On the cluster, it should be this. This is for our cluster, HPC. At Wesleyan, other machines are very likely to be the same thing. As we talked about, you can check the directory by actually CDing to that location and seeing what's there. A lot of times it will be in /bin anyways, so this may just work for you. And otherwise you can check out what other scripting language or the location of the path on your particular machine if you are not working on the HPC. So this would work for any Linux machine. Information for the job scheduler. So the job scheduler's duty is to take all the requests from all of the different users and figure out who gets to go next. And so what we mean by scheduling it is we mean by actually sending the job to actually start calculating. And so it's kind of like this. It wouldn't really make sense if somebody doesn't really need very much or very complicated equipment and they just have a short job to get stuck waiting in line for a long time behind somebody who is requesting perhaps some more specialized equipment. And so what we want to do is we want to move people through to get their jobs running more quickly based on what resources are available on the cluster, so that we have fewest people waiting in line and we maximize the use of what we have. So for example, in my group, we have some jobs that are going to need to work on the GPUs, the graphical processing units, and those jobs will require a considerable amount of memory. So we cannot just run it on any node on the computer. We would want to send it to a particular one. And so by using the configurations, we will be able to tell which one we could send it to. And so we're going to need the B sublines in order to actually specify what it is we're asking to use. Now, other times we might not really need to do a very complicated calculation, like maybe I'm just doing some data analysis, and a lot of these are really quick and short and really don't need to use a GPU. So we might be able to submit that, for example, to a different queue like the TinyMem or so on. And then we could make use of that instead. So the scheduler's duty then is to figure out, okay, what are all the requests that have been being made? Who made the request first, and what hardware is actually available for the job to run on. So the idea is that when I'm standing in line, I'm going to be waiting in line until I'm the one whose turn it is and the equipment that I am requesting is available. So the B sublines are used to select the important information about how the job will be run on the cluster. They can be used to configure the job and request the hardware that I need. So -Q selects which queue is requested. So as we talked about, the queue is linked to specific compute nodes or those back nodes that are actually going to do the job, because the head node, which is running the job scheduler, will not be doing the calculations. I mean, it's possible to do that, but the system administrator will be very upset. And also the head node is really not for calculation. The head node's job is to send back information when you type at the command line. So like when you type ls, the head node is telling you what the content of the directory is, right? So the head node is really for that, and it's really not designed for computations. And this is why we send things to queue, so that we then access those back nodes, which are designed for heavy duty calculations, because they have much better resources available to them. So you're going to need to know which queue you want. So we talked a little bit about which queues might be appropriate for you. If you're still confused on that, a good bet is to just talk to others working in your lab who are currently running calculations, and they should be able to tell you which queue is appropriate for your job. -N will mention the number of nodes you're running. So for regular jobs, you'd select 1. If you wish to run on multiple nodes, meaning you're planning to run in parallel, and you need to have parallelized code to do this, otherwise you'll just be blocking up nodes and running only on one of them, you would select N is greater than 1. Obviously, you can't use more nodes than exist on that machine, and selecting more nodes does not automatically cause your code to run in parallel. You actually have to have code which is compiled to execute in parallel. So if it hasn't been written that way, just picking more nodes doesn't make it all of a sudden become parallel. If your code is not designed to run on more than one, it will not speed up the execution either, because it will still only be running on one node while you're blocking up other nodes that are doing nothing. So please pick the correct number of nodes. If you're not sure, you should probably pick 1. And if you want to get more information about the parallelized version of code for your particular use, then you should talk to your lab members, or you may also find some information about that on the lab wiki. One clue you might find for this is if it has a MPI run, then it's likely you do have the option to run your code in parallel. -R selects the resources to be used. So this is in terms of the hardware resources. So by default, your job would run on a CPU or a central processing unit. These are pretty quick these days, and some jobs, in fact, actually are designed to run on the CPUs, but the GPUs is for the graphical processing units. And if your code, again, is designed to be run on GPUs and has been compiled to do so, then you may be wanting to request a GPU. So this is what you would do. You want to specify how many GPUs you are requesting. So it is possible to execute on more than one GPU at the same time. So your code may be parallelized, and it may be optimized to run on the graphical processing units. So again, you need to know what kind of code you're running and how it can be run. And you need to select the correct version of your code to run in order to reap the benefits of doing this. Mem is going to indicate the amount of memory that is requested. Span hosts indicates across how many hosts your job should run. So generally you want 1 because the communication between the different hosts will be slower. So the hosts, by that we mean the same thing as when we say the back node. So this means like a computer box. So some computer box may have multiple CPUs. It probably has more CPUs than GPUs, but there may be 1 or more GPU on that particular box. And which box or machine you get to depends on which queue you sent your request to. And so you need to tell how many GPUs you're requesting. And so if span host is a number larger than 1, what that means is that you could actually be going between different compute nodes or different back nodes, different actual computers. And so that may seem like a good thing to do, and it might speed up your job, but on the other hand, it may not. And the reason for that is because the communication within just one is pretty quick, but the communication between them can be slow. And so over parallelization or attempts to use multiple machines may in fact get bogged down because the network traffic is slow. So it's not always any good to pick a number bigger than 1. So we do have highly parallelized code. It can run on multiple GPUs, but we really only want to run it on one host so that it's faster. And that's what we pick. So I always pick 1. Now we also can put the information into the bsub lines. So here are some things that we can do. So the bsub command will have the -J flag. This is the job name. So conventionally it's chosen to be the name of the current working directory because first of all, that's going to almost certainly be unique. Although if you don't use your full path, it may not be, but you've probably chosen your directory name carefully to be descriptive of what's running and what the project is. So by convention, that's usually what we pick, but in fact, you could put whatever you want there. That's when your job is running and you want to check on it, that's what will be displayed. So it's useful that it's unique and that you will know what it means when you just glance at it. -O, this is the lowercase letter O, configures the name of the output file. This is the output from Unix and not the output from any programs you may run. Whatever would have displayed on the screen at the prompt will be directed to this file. So the caveat to saying this is only the output from Unix is not completely true because you could get output from your program that would have displayed on the screen in Unix. So the origin of it may have been your program that got passed to Unix. So maybe it's more precise to say that it's anything that Unix produces itself or that gets passed to Unix, which it normally would have shown to you if the monitor were on. So because you're going to submit your job and then it's highly unlikely you're going to sit there and watch your job run. So some of ours run for months and I may not be sitting at my computer when the output comes onto the screen. And so the better thing to do is to specify the out file and that will collect the output at whatever point. You can also have some things that on purpose go to the output file to indicate the progression of your scripts, which could be very useful. The -E file or flag is going to configure the name of the error log. This is the error log from the system, so it's going to report any issues that the Unix encounters when it's trying to execute. It's not going to necessarily report on the errors running with any programs that you may call from within your script. So if you're running a program and that program throws an error, it's likely that that one will land in the output file on the -O flag because it will be something that would be passed to Unix, and then all of the things that Unix would normally handle go to the -O file. So you may find errors either in the -O or in the -E. The -E is going to have the errors that pertain to like the actual execution of the file. Like if your the path to execute Gaussian is wrong, then you would find the error in the -E because that's something that the system was trying to do. Whereas if you had something like, let's say you've launched Gaussian successfully, but now Gaussian is trying to read a non-existent input file, that's an error that's generated by Gaussian. So that error is much more likely to wind up in the -O file because that's an error that's going to be, that would have been sent to the screen and now is being sent to the output. So at the end of the day, you should get in the habit of checking your -O and your -E files, whatever you configure those to be when you have a job that is problematic, or really just to check on things whenever you run the job. So let's try to put all this together into a script. Here's the shebang line at the top. Now I'm going to have a comment here. Notice I put lots of pounds here just to make sure that it gets blocked. And now we're going to have the B subline. So the B sublines begin with the pound, a single pound symbol, and the keyword B sub. And then we're going to go through these flags, which we have just talked about. If you put multiple pounds, that will protect it from the schedule from actually reading it. So for example, in this case, I am planning to use the Amber 128Q, but sometimes I use the MWGPU-Q instead. So I've just pounded that out, so it's not going to work this time, but I could easily change the selection the next time I want to use this script by putting more pounds in the B sub minus Q Amber 128 and decreasing the pounds here to just 1. So it's just a useful way to keep track of information and make it into a comment that I might wish to use later. So the minus N again is the number of hosts, and so we're using 1. Now this is the minus R for the resources. I'm using 1 GPU, and here I've specified the number of the amount of memory that I want, and then I have the span host equals 1 again, which matches what I put on the N1 over here. Here is the minus J. So this is the job name, which I have chosen to name after the directory that I'm working in. So this happens to be a certain project. And then I have configured my minus O and my minus E files, so they will be called out and ERR for out and error respectively. They'll just be text files. Path configuration, libraries, and environment variables. These are all things you will need to include in your script, and they are going to be very specific to the program you wish to run. There is more information on Hank's wiki about this, and a lot of these things are really going to be things you would get either from like a user manual, or you might get it from the cluster, or the wiki pages, or perhaps an even better place to get these from would be from others who are working in your lab that are running a similar calculation so that you can see how the resources are being used. Programs you wrote yourself to be run through bash scripts are unlikely to need any of these resources unless you have specifically programmed them to need them. So for example, if you make a bash script to execute something, you're not going to need to worry about this. Like we wrote the some scripts for like hello world and so on, like those kinds of scripts. Don't worry about it. You don't need this. But some programs that do need these things are a lot of the commercial software, Amber, Gaussian, MATLAB, Mathematica, LAMPS, and there are probably others as well that are out there in use in the various labs. And so you will need to specify these things. The paths configures where to look for program-specific directories, such as the software packages bin. The libraries, this is going to load libraries needed for your specific job type. These may vary between machines since they may have different hardware. So that's something to be aware of. So if you submit something to a different queue, that means you could wind up on a different back node. Almost certainly you will wind up on a different back node. And because they have different hardware, what you put for the library files could be different. These are needed for running the multi-threaded and or parallel jobs on the CPU or GPU. They may be needed for your specific program, especially if you're running any of these. The environment variables are variables that are just in the bash script. So when you write programs yourself, you may in fact be creating some environment variables. These are the variables set up for running the job. The environment variables often point towards specific paths, and these will also be job specific. So let's take a look at some examples. This is an example for the configuration of Amber 16. And so here we see that I'm going to be using CUDA capable devices. This is for NVIDIA using the GPUs. And I am also going to be doing the MPI run. So I'm going to need to set up these paths. So we use the export command because this is how bash actually makes the variables become usable. So here we have the path variable and we have the load library path. The another version of the path variable, and another for the load library. Notice that when you actually do this and you use the colon, what this is going to do is it's going to add on anything else that you say. So you're telling it where all the places you want to look for that file could be. And so it's going to walk along that path and look to see the first location of where that is. So for example, if you just use the name of a script and you don't execute with the complete path, it will use this. You might think, oh, well, I should just use the full path all the time. But the issue is that inside the program, especially the commercial programs, they're often calling other parts of the program, other bits of code. And so when the program is written in, they're not going to know where it's going to be installed on your particular computer. So it's going to be a relative path. And so it needs to know like where that relative path goes to. And they would tend to be predicated by the same path up to a certain directory, such as the bin. And so this is why we need to configure these things here. There's also this concept of the scratch directory, and this is a big thing for running the Gaussian code. And the reason is that you may want to write your files on the memory of the backnode computer on which you're actually doing the calculation. Now, the whole point of submitting something to the queue is that you don't necessarily know which back computer you're going to get. You'll get the first one that's available. So you can't hard code your paths. And so that's what this sans scratch or anything about scratch is going to be about. It's going to be about configuring those paths on the local machine. And oftentimes how those are used is that one would write something to the local machine, but of course that's not your computer, that's a cluster computer, and so eventually that data would get deleted. So what you do is you write to that one, and then you could copy it once the calculation is over. You would copy all of the data. Oftentimes the reason why we do this is because writing across the network, so for example going from the back node to write to say your home directory or whatnot, is going to be a very slow process. Gaussian is notorious for writing extremely frequently, and so if you try to run this over the network connectivity, it slows down the network for everyone, not to mention make your job really slow. So what we want to do is we write to the scratch, which means that whatever computer it's calculating on, it uses that memory, it writes to there, and then you would move your files as part of your script after. So some jobs need this, not all of them do. We did set this up for Amber 16. This is not in wide use right now, but this is how you would set up such variables, and that's what they would be used for. And we also need to set up the environment. So there could be some paths to set up for this. So here we are adding this to the path variable. Also, we have the load library path, and we are also sourcing this script, so to source a script means to actually run this script as though I type like / in the name of that script. So this script may be causing some environment changes, and so this is a way to standardize all the things that a user should be adding to their path and so on. So there could be some additional commands in the ember.sh so that all users could easily do that. So you might see that not everything is going to have source. You may explicitly list them out in here as well. All right, so how do you know which configuration information needs to be included? We have said that a lot of these things are going to be dependent on the calculation type that you are trying to run. So you can ask your research advisor, you can ask your lab mates, you can ask someone who's running the program you want to use for a sample script. You could share your scripts in /bin between lab members so that everybody's using the same script. You may look on the wiki for your program of interest. Hank keeps a wiki. There are sample bash job submission scripts available for major programs running on the cluster. Also, sometimes the vendors may have some sample scripts available to you. So for example, the Amber program may have some sample bash scripts for running things. Also, there are people who maintain web pages on on how to run Amber that would have some sample scripts in them. So you can look for those sorts of things in your respective resources as they apply to you. There's also going to be job-specific commands. This appears below the configuration information, and this is what will actually run the job that you want to run. Thus far, we've really only talked about configuring, well, okay, the Shebang Line for the programming language of the script. Then we talked about the B sub lines, which is going to configure what the scheduler will see. And then we talked about configuring the libraries, which is for the code that you're actually going to run, but we haven't actually done anything about actual code that's going to get run. So that's the interesting part. Will actually do a useful calculation for you. So you want to be sure that you include that in your script. This is probably the most important and most interesting part. So you can run as many calculations as you wish in an individual script. You just put them one after the other. So maybe you know how to program in Python, and you would be very familiar with having multiple commands inside of your Python script. So the same thing is true here. Be sure to include your job-specific inputs and outputs. This may include wrapper scripts for MPI run parallelization, in which your job becomes the input to that script call. So for example, we see an example of this. We are using a wrapper script for the PMEMD.CUDA. So this means this is parallelized code that we're running. This is actually the parallelized version of Amber, which is going to then be running faster, but we need to apply this wrapper to it before we can execute this. Then we're going to need to specify all the user-specific parameters that are going to pertain to the job that we actually want to run. So I'm not going to be an expert in every single kind of job that could run, but the idea here is that I know that if I'm running an Amber calculation, that I need to have these various things. This is my energy minimization input. This is an output file name for an energy minimization. Here is a file called a parm-top file, which may not mean anything to many other of you. It's just a parameter file and so on. But all the different programs are going to have their different requirements in terms of what you're going to need to specify for the input types. And there may also be different kinds of input for different kinds of runs that your program is capable of doing. So what you want to do then, again, is just make sure you put in all the things that are going to be specific for what you need. Now, this input line is actually really quite long, and so it actually does wrap all the way around here. So this is all one line. Notice that it just wraps like that, and that's fine. That doesn't create any problems. One thing that I would mention that can become problematic when you're entering these into the scripts is that sometimes on screen you will see a little slash appear on the right hand side here to indicate the line continuation. And if you resize your window, sometimes that slash will actually manifest itself as an actual character in your path that was unintended. And so don't resize your windows while you're typing your paths, because in your long lines, because you could have this thing happen. Now, let's say that that does happen. What do you need to do? Well, you'll probably recognize it as some very strange backslash in the middle of your in the middle of your line, and so you can actually just go there and edit it out. And you'll want to make sure you just size your window to whatever you want it to be before you get started with that. But it's not a problem if it appears when your line wraps and you don't resize your window. It's just that I have seen it become a problem if you write it and then you make your line, the width of your window shorter, because that wrapping line character will jump into the lower line when you squish it, and it shouldn't be there. So just be on the lookout for that. On the example down here, it shows running a CUDA-enabled parallel code particle mesh eval molecular dynamics simulation. This has the MPI wrapper, which we see right here for the MPI right here. And it's specifically written for the Amber 128Q. And the Amber 128Q specifically then sends jobs to the node N78. And then the machine to which the Q Amber 128, well, that's where that one links up to. So yours may link to a different node depending on which one you want to send your job to. Suppose I need to test my code before I put it into a script. You may wish to test your program's input and output files with a short test run to ensure it's working correctly. Please do not run your jobs on the head node. As we mentioned, the job of the head node is to respond to the terminal requests like ls, pwd, and all those things, and also to execute the scheduler, not to be calculating jobs. It's really not set up to do that. It doesn't have the hardware to support it, and it will slow down the cluster for everyone. So you should not run it from the command line when you log into Cottontail or Cottontail 2, and because it can destabilize the cluster for all users. It's generally acceptable to do test runs of scripts on the head node if it runs for under 10 minutes, because then it's, not too taxing, but do use good judgment and don't overdo it. It's better to run your job on one of the backup nodes if you must test it from the command line. So what you could do is you could SSH to Petaltail, Swallowtail, or any other of the backup nodes. So let's say I'm logged on to Cottontail and want to test my Sander run to be sure all my input and output files are working correctly before running the script over the weekend while I'll be away, because I might submit my script. It might be sitting in the queue for a while. Maybe there's a 2-hour wait in the queue, but I'm already going to be long gone on a camping trip, and my job might crash because, I had a typo in a file name. That would be a very unfortunate situation, because I will come back on Monday morning and will be no further along than at the moment that I left. So you might want to check your scripts before you actually run them. And so what you could do is test it out on Swallowtail instead of Cottontail in case there's bad input. It's too long, other unknown problems, who knows what could go wrong. So here we would do SSH Swallowtail, and then I would CD to the directory of my particular project, and then I could run Amber like this. So this will run on the head node, but it's not the main scheduler, because I am now on a different node on the cluster, which will be like the head node, but not exactly like it. This generally works pretty okay, but there are certainly instances where the hardware differences on the back nodes may not be the same as the hardware specifications on the other head node, and also the specifications of the hardware on the head node may not be the same as the one on the nodes which you will actually execute as specified by your by the queue that you pick. And so really running things on the head node is not the best test, but if you must, running it from one of these other nodes is really the proper etiquette for testing things, or make it a very, very short run that you can run in under 10 minutes so you can test it out without getting in the queue. But then even that is still not a good test, because you're not actually on the node that will actually run it. So if the problem is of that nature, you could run into issues still. But anyways, this is how you would do it. If you do run extensive jobs, other things, run your scripts and so on the head node, the system administrator will and does terminate illegal jobs because it destabilizes the cluster for everybody. So please don't do it. So then, bringing everything all together, this is what a script could look like. Here we have the shebang line at the top. Then we have some comments here. We're now going to have the bsub configurations with bsub of the queue, the number of nodes, the resources needed, the name of the job, the output and error file names. Then we're going to have some other comments in here to help the user. We next move into this section that we're going to specify the job specific libraries, paths, and environment variables. And then finally down at the bottom, we would specify the actual job which is going to be run, which here is illustrating the use of particle mesh ewald molecular dynamics running on a CUDA capable device that is a GPU to run a calculation called an energy minimization. These things down here, of course, are just part of the editor itself. It's just how the terminal window looks. All right, so now with that in mind, the next thing we want to talk about is the queuing system itself. The bsub command is going to be used to submit your job to the queue, otherwise known as the scheduler. A queue, of course, means a line. So we got this idea of we're queuing up in line in order to use the resources on the cluster. Make sure you have made your script executable. Don't forget to do that, chmod u+x if you have not done so already. It's a common mistake. You could miss that. The header will be red and your job will be assigned to the queue specified by your -q flag. When the resources requested in the -r line become available on a machine served by your queue, your job will then begin to run. So you would do b-sub, and then we need to use the less than symbol, which is the redirect for input, and then you provide the name of your submission script. For example, that one we have just looked at a few slides back. Do not give the name of your program, such as Amber here. It will read it from inside the script. Only use the b-sub with the bash submission scripts. Other scripts, such as a Python script or the input script for running Amber, Gaussian, MATLAB, those are not here. You need to be using that bash submission script with the b-sub lines and the libraries and so on specified. That's the one that goes here. The job ID. So each job, when it's submitted to the queue, will be issued a unique job ID. And this is useful for tracking your jobs to know what is happening. So when you b-sub your job, like is being shown here, you'll get back a job ID, which you can see right here. And this is some particular job, and it tells us that it is submitted to the Amber 128 queue. How do you know if your job is running? Well, let's talk about how to check it. The command bjobs will report on the status of all the jobs being run by you. Here we see we have issued the bjobs command and we get this little table back. So it's going to have several headers running across the top, and then it lists all jobs that you are running. So in this case, I'm only running that single job that we just talked about. So I'm the user Kate there, and this is that job ID that had just been given to us before. It also appears in this table. So if you did not capture it in the instant that you submitted it, you can also get it from this table. This will tell us the status of the job. So the typical status is penned and run. So penned means that I'm waiting in line to get my job to execute, and run means that my job is actually executing. The queue reports which queue the job was sent to. So that should match up to what was on the -q flags. This says Amber 128. If you don't tell it, it will send it to TinyMem, I believe. And you probably, if you're on a different machine, there may be another default one. So you should tell which queue. And then this is the from host. So this means where was I when I submitted it? I was logged on to Cottontail. The execution host has not yet been specified because I'm in status penned. So I haven't been assigned to one yet. So once I am in the run status, then the name of the execution host, such as N78, the back node called N78 would appear here. And here we get the job name. So this was on your -J flag that we set up in the configuration. And then it also keeps track of the submit time. So you can have an idea of how long your job has been waiting or how long it has been running. When you issue the bjobs command and it no longer appears in here, that's how you know your job is done. Doesn't mean it's run correctly, but it means that it's no longer in the queue. So it's not waiting and it's not executing. So we would assume that then it is completed, perhaps with errors, or perhaps it is completed correctly. So how long do you have to wait? You could check the so-called traffic report to get some sense of how long it's going to take for your job to get assigned to a node. So this is not about how long it takes for a particular Gaussian or Amber job to run. That's for you to know from the kind of calculation that you're running. But what you might want to find out that's not so predictable is how long is it going to take for me to actually get my job to the status run from the pen status. So you cannot tell exactly, but there are some things you could look at that might be quite helpful in getting a sense of what's going on. So you can get a sense of the cluster usage given the time with the BQ commands and checking your queue. So for example, here I'm using the BQs command. So what's going to happen is I'm going to get a list of all of the available queues on the cluster. And so some of these have a higher priority than others. So test, for example, okay, so test is the name of our default queue in this printout right here. So this is why the priority is really high. The status here is going to tell us if that queue is available. So usually it should be, but sometimes a certain queue needs to be taken offline because there's some maintenance work going on by the system administrator. And so it may be that the status is closed. Also, if there's a planned shutdown of the cluster, a particular queue could be closed a few days before the actual shutdown occurs so that no new jobs get added in line. So that's another reason you may see a status other than open and active. It may be closed. And the max is going to tell you the maximum number of jobs that you can get here. There's also some other stats here. I'm just going to take you through the ones that are going to be the most pertinent here. So this is how many jobs that the queue could take, and this is the number of jobs that are this one, and jobs is the number of jobs is actually running on that queue. So for example, the test queue could take up to 48 jobs, and there are no actual jobs running there right now, and there are also no jobs pending, and there's also no jobs here. So end jobs would actually be the sum of the pending and the running jobs, and I think it may also sum the suspended jobs. So your job is probably not going to be suspended. That's a special case when your job needs to be stopped in mid-execution. But let's take a look at something else. So I've just submitted my job to MW128, I believe. All right, so here it says that we could have 648 jobs running on here. Obviously, all of these aren't going to be GPU jobs. So this number is pretty high, and this is because of the number of expected jobs that could also fit on the CPUs. So what we see is there are 228 jobs running on there right now, and that there are no jobs pending there. And so that means that all 228 of those jobs are running. So if I want to submit something to this queue, as long as the hardware is available, I would not have to wait in line because I could go all the way up to 648. Now let's take a look down here. This is the Amber 128, which actually I think is a queue we used. This right here is the job that we had just talked about submitting. So what we can, let there be light. What we see here is that there are 204 jobs, that there are 5 jobs total. There's 1 pending and 4 running. And so what may be happening, and so why am I pending? There could be up to 24 jobs on here. Well, the reason may be that the resources I need are not available. And I happen to know that this one has 4 GPUs available. And so these 4 jobs that are running here may well be my colleagues who are also using the GPUs to run their jobs. And so I may have quite a long wait here. And so if that were my situation, then I might start strategizing and thinking, okay, could I run this on a different queue to use different hardware? And so I might, for example, try to put it on one of these other queues in order to do that. So I put together some FAQs about queuing, because these may be some things that you encounter as you are actually trying to run some jobs. There are open slots in my queue. Why am I still waiting? Well, we've kind of just seen that in the scenario we looked at before. It may be that there are slots available, but not for the resources that you requested. So this often happens if you need to use a GPU, which of course are going to be very specific slots, and the number of slots being shown is for all possible slots, not just the GPU slots. So if the number of slots available is large and yet you are still waiting in line, the likely reason is because you've requested a GPU and there are not any GPUs available. So it's not going to send it off unless you tell it that you would run it on a CPU instead. But if you've requested the GPU, it won't release the job until a GPU is available. There may not be enough memory available for what you requested in your -R line. So anything that's running on the same node is going to be sharing the memory on that node. So some of the memory footprints on some of them. Some of the nodes are larger than others. And so you need to be sure that first of all, you choose a queue that feeds to a machine that has adequate memory for the usage that you need. And also, if somebody else is already running on there and running a particularly large job, it's possible that there's not enough memory left over for what you're asking for. So when it is going to allocate the memory, when you set up the memory allocation, what it's going to do is it's going to block off that amount of memory and nobody else can use it, even if that memory in that particular instant isn't being used. So it basically is determining how much that's going to expand and gives a limit for that. So when you've exceeded the total amount of memory that's available, the job will not go into the queue until that memory becomes available. Another thing you could consider doing is you could change what's in your minus R line if you could get away with using less memory, but generally you should be requesting the amount of memory that's needed for your job and not more, so that we can make maximum use of the cluster. If you're requesting multiple nodes with the span hosts equals 1, which you requested could be available across several hosts, but not all on one specific host. So that's another thing to be aware of. How can I get my job processed faster? You could consider killing the current job and sending it to a different queue if it's less busy and you're able to do that. And that, of course, is going to depend on where you're able to run your job. Some jobs cannot be run on other queues because you require certain hardware and so on. But if that's an option for you, that's something you might want to consider. I forgot my process ID for a particular job. What do I do? Well, remember that we can use the bjobs command and that it will be listed right in that table. So you can just get it off of that one. And if you have used a good job in your -J to have descriptive process IDs, process descriptions, then you would quickly be able to tell which one is the one you are looking for, because they will be unique and will tell a certain directory. By the way, you should not be running multiple jobs in the same directory because you run the risk of overwriting files. So that's another reason why the -J conventionally is specified as the directory, because in theory that should be unique, because you shouldn't be running jobs simultaneously in the same directory, although of course it's possible to do that, although we would certainly very strongly advise against doing that. I need to stop or pause my job in the queue while it's executing. How can I do this? So this is this suspend, which we had seen as the SUSP status. First, you need to put your job on hold using the bstop and the process ID. So we had the info on how to get your process ID if you're not sure what that is. Verify that the status is changed to USU spend, or that stands for user suspend. There's also the system administrator has the privilege of suspending your job, but when you suspend it, you'll see it as a use suspend as your status. This may take a few moments to take effect, so you can check with bjobs, and if you don't see it immediately, just wait a moment or two and try again, and you'll see it quickly. Then you can either kill the job, stop the execution, and remove the job from the queue with bkill. And again, you would give that the process ID. By the way, you don't type the brackets, you just type bkill and then the process ID. Or resume your job with bresume. So that allows you then to suspend jobs and to resume them. You might want to do that because you want to make use of the hardware for a different calculation without completely closing out the first calculation. The system administrator may do that when some work is going to be done that's light and doesn't require a restart of the machine, but there may be, for example, some memory may be unplugged or something like this that could cause some errors. So what we want to do is just stop the jobs from executing for the moment, and then they should be able to be restarted. So those are some possible uses you may use for the suspend. You can verify that it worked by using the bjobs, and then look that the job is no longer in the queue for bkill, which would mean you have killed your job, or that it's resumed running for bresume. You might kill your job if you realize that, for example, you had some error in your input that wasn't going to cause your job to crash, but that was causing it to calculate the wrong thing or something. And you might want to use that resource for something else. Sometimes we do make the mistake that we accidentally repeat a calculation or put the wrong input file. And although syntactically everything's fine, it may be, a repeat or whatever, and it wasn't what you intended to calculate. So you would need to stop, then suspend. You would stop your job to put it in the suspend mode, and then you would kill the job, which then would open that up to run another calculation or to let somebody else use the cluster. Even more FAQs, what other users are in the Amber 128 queue or whichever queue you're in? So I might be saying, who is blocking up my queue? I want to use it. So you can actually find that out by using the bjobs options with the -u, which specifies a user, and then you could use the keyword all. So what this says is look for all users, and then we can use grep. So this is a Unix utility that can be used to search those results for the phrase that you specify. So here we're going to do bjobs -u all to get all the jobs. So if you just left it at that, you would see all the users and all the queues, which is going to be very long. It's going to be probably hundreds of entries at any particular time, maybe around that. But what you can do is you can then pipe it to grep, which will allow you to search for the entries that only have listed with the bjobs -u all. You can then search for Amber 128, and then we get a much shorter list here. And I could look at this and see that there are these jobs running here. Lo and behold, they're all in Amber 128. So my colleagues' jobs are running, but I'm stuck in the pending mode because they are blocking up the resources running their jobs. And I can even get some idea. Okay, so here I can see that they're using N78, that back node, and I can also see the names they have given to these, so I can get some sense of what's going on. So maybe if I have an emergency, like I have to give a talk tomorrow and I must run a calculation, now I know who I could ask to suspend their job so that I could run mine quickly. Or if somebody's running illegally or whatever, now I know who I need to talk to because I can look at the username over here, and I also get some sense as to what's going on. Now, these people happen to be in my group. I might even use my read permissions to look at their output files to get a sense of how long their jobs have run. And since they're probably also running empty jobs, I could probably have a pretty good idea as to how much longer their jobs are going to run by reading their output files, which you can do in the shared environment if the permissions allow. I need the results from a colleague's job. Is it done running yet? You can check for all the jobs being run or pending by using user with similar strategy, and you can put the username of your colleague. So maybe my colleague is running a calculation, right? And I'm looking for the output to add to my graphs that I need to make for tomorrow's talk. Is it finished yet? So what I can do is I can do bjobs -u, and then this is the username of my colleague, and I can check to see what they are in fact running, and I can see then whether or not this has been removed from the list here, in which case then I would know that it was completed, but maybe they're running that for me and I could see, no, it's still running. So I'm not going to be getting their results yet. So that's how you can tell. What to do when the job fails? The first thing to do is to determine whether it failed because of a problem with the cluster, like a Unix problem, or because of a problem of actually running your particular program. So as we've mentioned before, we have these two important files, the -e and the -o flags in your bsub commands, which we can find in that submission script. So what you're going to do is you're going to look to see how you called them if you forgot. If you did it by default, they'll be called ERR for error and out for the output file. ERR, the error file, is going to contain errors that are generated by the system, and the out file is going to contain output from the system, from Unix, or anything that is passed to the standard output that would have been sent to Unix as the standard output. So oftentimes you'll want to look at both of these, and then you're going to need to figure out, okay, where did the problem originate? So look in the output files from your program. as well. So your program may have some kind of a log file or such that it writes, which is separate from the -e and -o, which are the system-wide error files. You can look in the log files from your program to find information about what your program actually did. Now, it's also possible that the error happened at the system level and that it never actually ran. Like, suppose I'm supposed to run a program called Amber, but I misspelled it. Okay, so the script probably ran fine, except that when it tried to execute Amber, that created an error. So Amber itself never ran, and so I may not have an output file from Amber, which normally would create a log file. So that's one clue that your problem is probably at the system level or at the level of calling your particular program, and it's unlikely to be the execution of your program itself. So if you do get a log file, that can also provide a lot of information in terms of what's actually been happening inside of your program. You should have your program set up so that it's verbose and that it is providing you with some output so that you can tell what's going on. If your program does provide output to the standard out, like prints to the screen, it will be redirected to the system output file. Generally, commercial software is not going to do that for most things. Things that are written to the standard out are going to be pretty serious errors that are terminating the execution of your program. So you may find something like that on your -o flag, but generally you're going to be looking for things from your program inside of the log file or other output file or files that your particular program will configure. So for example, my program may be configuring an output data file for energies of my system if I've configured a run to do that. And I also get the log file, and I may also get a trajectory file. So there's all multiple output files I could be getting, and each of your programs will be doing something unique to that particular program. So knowing what output files your program creates, looking to see if those files exist, and looking at the size of them. If you get an output file but the size is 0, that clues you in that something may have gone wrong. Go and look in those files and see what it says to get some idea of what's going on. Look in the -e and the -o flag for errors like wrong file names, incorrect libraries. Those kinds of things are likely to show up in either your -e or your -o file to help you debug what is going on. So we are, as of fall 2022, going to be switching over to Cottontail 2 as our new head node, and that will be executing a new scheduler called Slurm. And so it's important to get a preview of this because we will be switching over in a short period of time. Cottontail 2 is our new head node, which is going to be running alongside Cottontail. So Cottontail plain is now becoming deprecated and can be used as a backup node. And so Cottontail 2 will soon take over most all of the queuing tasks. For present, we have queuing running on Cottontail and test phase on Cottontail 2, but these things are moving over onto Cottontail 2 a few at a time to transition in for Cottontail 2 to take over. You can SSH to Cottontail to submit your jobs. A limited number of queues are coming online to Cottontail 2, although that number is now increasing. There's some differences in the syntax of the submission scripts because they are going to be a different software, but they are quite similar. You can read about the updates on the phasing in of Cottontail 2 on this DocuWiki right here. You can go and check that out. This is part of Hank's wiki to keep you abreast of all the things that are happening in the cluster world. So we've today talked about the submission from Cottontail, and here what I've attempted to do is to match up the command that we have talked about for Cottontail to what it will be in Cottontail 2. Now, most of these should switch over pretty readily. Bjobs will become just jobs, and bqueues will remain bqueues. bsub and some setting will become sbatch, and bsub and the less than and run.sh is going to be sbatch run.slurm. So notice that there is a syntactical difference. This is what you use to actually submit it. So this one uses the redirect to get the name of the script, whereas this one takes it as an argument on the command line. So it is a bit of a different way of doing that. So this is a sample file header for Cottontail 2. Notice that I took this off the DocuWiki, so you can also check the DocuWiki yourself to look to see additional information and perhaps some other examples of scripts. So we could expect that there will be increasing number of sample scripts as we are bringing more and more things online with the Cottontail 2, so that you can go there and get a sample script that will work for your program. Now, I would suggest also that you simply just ask others in your lab who are running or developing them for your lab. You can reach out to Hank to get some pointers on this, and also you can find examples of Slurm submission scripts by just Googling that, and again, just checking with your vendor who is likely to supply some sample generic scripts for this purpose. So then in summary, we have now completed day 3 of the 3-part series. On day 1, we took a look at high performance computing here at Wesleyan and in general. On day 2, we talked about working on the cluster with the text editors, and we learned a couple of Unix commands, and we also compared and contrasted some popular editors that you could find on clusters. And today we got into the bash scripting. We talked about the queuing system. We've learned how to write some simple bash scripts. There's of course much more that one could learn about this. It's a whole scripting language with looping and if statements and many other things that you would learn about in a computer programming class. So we've pretty much stuck to the basics for what you would need to be writing some very simple input scripts, but you could of course learn more about that. We have learned how to submit these scripts to the queue, and along the way we have also learned some more Unix commands. All right, well, I do hope that this has been really helpful for helping you get up and started with working on our cluster. This has been set up for work on the Wesleyan University's high performance computing cluster, but these concepts should be pretty universal for many other situations. So if your lab, for example, is also using some other offsite Unix kind of shared systems, using some time on some supercomputers elsewhere, then a lot of these concepts also should be working for that too. And you may also graduate and move on to other institutions where you are working on Unix systems, and this should get you at least in the ballpark of having an idea of what's going on for those so that you can get started. All right, well, thank you so much for joining us this evening. I hope that this has been helpful, and we hope that we will see you again for some additional tutorials on how to work with Unix and other exciting topics that are related to high performance computing and molecular dynamics simulation. We'll see you next time.